Welcome to the Improving and Combining Functions lesson. Today, we'll start with higher order functions. Then we'll cover Lambda functions, precedence and associativity, Curried functions and partial application. And finally, we'll learn about applying and composing functions using the $sign and dot operators. It will be a long lesson, so make sure to grab a cup of coffee before studying. A higher order function is a function that takes other functions as arguments or returns a function as a result. Because we can pass functions as inputs, return them as result, and assign them to variables, they are like any other value. So we say that functions are first-class citizens. Let's start with a classic example. Imagine that you have a function you usually apply twice for some reason, like this. Here we have a complex function that takes an integer and returns an integer, just takes an integer and adds 1 to it. Then we have function 1 that uses this complex function twice. First, it takes the input and applies complex function to it, and then applies complex function to the result of that. Then we have complex function 2 that adds 2 to the input, and function 2 that takes an input, an integer, and applies complex func twice, first and second, and adds that to the same thing to the right side. Applies the complex function 2 to the input, and then applies complex function to the result of applying complex function to the input. This is an exaggerated example, but you can see how a pattern starts to emerge. You always use the complex func 1 and complex func 2 twice. As soon as we saw this pattern, we realized we could do better. What if we create a function that takes two parameters, a function and a value, and applies the function to that value twice? We can do that simply by writing this. Here, the type signature of apply twice is different from the previous one. This part indicates that the first parameter is a function that takes a value of type A and returns a value of the same type. The second parameter is just a value of type A, and the whole apply twice function returns a value of type A. And in the body of the function, you can see that it takes the first parameter, the function, applies it to the second parameter x, and then applies the function again to the result. So we are applying function f twice. And that's it. We created a higher order function. We can use the apply twice function to simplify the previous code like this. Here we pass the complex func 1 and the initial value to the apply twice function, and it will be applied twice. And here we do the exact same thing in two different locations. This is a simple example, but higher order functions are an extremely powerful feature. So much so that they are everywhere. In fact, you could create your own domain-specific language using higher order functions. But let's take it step by step, and let's start by using two higher order functions that come with Haskell. Let's start with the filter function. As you can see, this function takes a predicate, a function that returns a boolean, and a list of elements of type A, and filters the elements of the list given the predicate. So, for example, if we want to filter only the even numbers from a list from 1 to 20, we could do something like this. Here we'll take the filter higher order function, and we pass a list that goes from 1 to 20, and a predicate that checks if a number is even. If it's even, it's true. If it's not, it's false. and we get the final result, only even numbers. Or for a more involved condition, we could filter from a list of fruits only the ones that contain the lowercase a. Here we pass the temp function that we create in the where block. And because we're filtering for lowercase a, for all the elements in each value, and each value is every single letter inside the string, we get only the fruits that contain the lowercase a. Another example is the any function. This is a simplified signature. This function also takes a predicate and a list, but this one checks if there exists any element in the list from which the predicate holds. For example, if we are checking if any of the elements of the list is greater than 4, we can do something like this. If only 1 is greater than 4, any returns true, else it returns false. A more realistic way to use any will be to check if we have any cars left in our car selling website. Here we have a list of tuples of two values, meaning a pair, that contains the brand of the cars and the quantity. Then we create the bigger than 0 function, where we are pattern matching on the tuple to extract the number of cars and check if it's greater than 0. Then we are using any to check if any of all the pairs in the list has at least one car left. Okay, we saw plenty of examples of functions that take other functions as parameters. But what about functions that return functions as results? We will get there. First, we'll learn about Lambda abstractions and Curried functions. The term Lambda function comes from the mathematical system called Lambda calculus. It's an intriguing and powerful subject by itself, but today we're going to look at it from the practical programmer point of view. A Lambda function, also called anonymous function, is a function definition that doesn't have a name. For example, here's how a Lambda function that takes two arguments and multiplies them looks like in Haskell. A Lambda function consists of 4 things. The backslash at the beginning tells us that this is a Lambda function. The parameter names, in this case x and y, that the function takes as inputs, then the arrow that separates the inputs from the body, and then everything after the arrow is the body of the function. Most modern programming languages also have anonymous functions, but not all of them work in the same way. So, why should you care? It sounds useless because how can you use a nameless function if you have no way of calling it later? Actually, it's a powerful component of the language. Throughout this course, we'll encounter many situations where Lambda expressions are practical. For starters, you can use Lambda expressions to avoid naming functions that you will only use once. This is useful in and of itself, but it really shines when working with higher order functions. For example, take a look at this previous example. That bigger than 4 function won't be used anywhere else, but it will linger in our environment forever. Also, it's an awfully simple function. The name is longer than the body. By using Lambda functions, we can create and use bigger than 4 as a parameter for any, all at the same time, like this. We can also use Lambda expressions to simplify other functions. Let's review the fruit with a function. We can simplify fruit with a by removing the temp func and replacing it with a Lambda function, like this. And of course, because Lambda functions are just expressions, you could use them anywhere an expression can be used, even by themselves. If you need more examples, keep watching. Lambda functions will be a valuable tool to easily visualize scoring. Right now, we'll take a few minutes to learn about precedence and associativity. Precedence indicates the priority of an operator, denoted by a number from 0 to 9. If we use two operators with different precedence, the one with a higher precedence gets applied first, meaning that higher precedence operators bind more tightly. We can get the precedence of an operator with the info command. Here, infix 6 plus and infix L7 star are called fixity declarations because multiplication has a precedence of 7, which is higher than the addition precedence of 6. This operation will happen earlier, so the final result is 7 and not 9. And what happens when two operators have the same precedence? This is when associativity comes into play. When two operators have the same precedence, the associativity tells you which side, either left with infix L or right with infix R, will be evaluated first. For example, the addition operator and product operator have left associativity, which means that they evaluate the left side first. Meaning that if we encounter something like this, it will evaluate first the leftmost expression, then it will keep propagating to the right, like we indicate here. The cons operator has right associativity, we can see it here, which means that it evaluates the right side first. That looks like this. And there are also operators like the equivalence operator that has no associativity, as you can see here. Which means that if you use more than one, you need parentheses to indicate the order. Else, you will get an error. And of course, you can change the evaluation order using parentheses. Finally, we can define precedence and associativity when creating our own operator, like this. Here we are creating the plus 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 operator that just adds two numbers. And then we are setting the fixity of the operator as a precedence of 7 and left associativity. So now, if we replace the plus with the plus plus plus, we get the result of 9, because it has the same precedence as multiplication and is left associative. So this will happen first, and the result of this will be multiplied by 3. An important note is that operators without an explicit fixity declaration are infix L9. And function application, that means the white space operator, always has the highest precedence. Imagine that it has a precedence of 10. Now we're ready to look at curried functions. Currying is the process of changing a function so that rather than taking multiple inputs, it takes a single input and returns a function which accepts their second input, and so on and so forth. And here's the kicker. In Haskell, all functions are considered curried. That is, all functions in Haskell take just one argument. To exemplify this, take a look at this function. It seems like a multi-parameter function, but there are hidden associativities in play. We know that function application, the white space operator, always has the highest precedence and associates to the left. So, if we make that obvious, we get this. If we check the fixture of the function arrow, we see that it associates to the right. So, a more explicit way of writing the signature of add3 is like this, which perfectly corresponds with the function definition. But just to make it painfully obvious, we'll make currying explicit using lambda functions. Starting with the previous definition, we will move each parameter from the left side of the equal sign to the right side, creating the same function several times but written differently. So, starting with set, the outermost parameter, an equivalent add3 function that does exactly the same as the original can be written like this. Now, add3 is a function that takes two numbers, x and y, and returns a function that takes another number, z, and adds the three together. If we do it again for the second value, we get this. Now, add3 is a function that takes one number, x, and returns a function that takes one number, y, that returns a function that takes one number, z, and that adds the three together. And if we do it one more time, we get that add3 is a name that returns a function that takes one number x and returns a function that takes one number y, that returns a function that takes one number z, that adds the three numbers together. That was quite a long journey, but we managed to make currying explicit. And now, the way signatures are written makes way more sense. Each time you replace one parameter, it returns a new function as a result. That is, until you replace the final one that gives you the final result. And because the function arrow is right associative, we can remove the useless parentheses in both the signature and the definition to get a cleaner code. And now, for example, if we apply the function to three parameters like this is what happens step by step. I re-added the parentheses for visual aid. This is the initial function, and when the first value is applied, it returns this function with the value of x replaced. Then when the second value is applied, it returns this function with the second value replaced. And finally, when the third value is applied, it returns the last body of the function with the last value replaced. So, besides being a cool conversation starter at the club, how is this useful for you? Well, with uncurried functions, if you provide fewer parameters than the ones required, you get an error. But because in Haskell all functions are curried, you can take advantage of it to use partial application. Partial application in Haskell means that you provide fewer arguments than the maximum amount the function accepts. The result, like we saw earlier, is a new function that takes in the rest of the parameters you did not provide to the original function. As a practical example of how this is useful, let's say that you have a function used to create an email in the format name.lastname@domain. The parameters you provide are the domain, the name, and the last name. This function looks like this. But now your company has two communities as clients, which have two different domain names. You don't want your users to write out the domain name every time. So you create two functions where you partially apply the domain names, like this. In this case, we create the new function createEmailToken that takes the createEmail previous function that takes the domain, the name, and the last name, but it partially applies the domain. So createEmailToken, we have the createEmail function with the domain already applied. The same for a different domain. And finally, we can use these new functions with partially applied createEmail by providing the rest of the parameters. Notice that this is possible because the domain is the first parameter in the function createEmail. So the order of the arguments matters. If, for some reason, the parameter you want to apply is not the first one and you're not allowed to rewrite the function, you can create a helper function like this. In this case, we create the createEmailJohn function that takes the last name and the domain and partially applies the createEmail function with the name John. And without partial application, we just create the same parameters, but we rearrange them in the way that is more convenient to us. And because operators are just infix functions, we can also partially apply them. For example, recalling the previous example of a higher order function, in the function we pass as the parameter, we need to compare if the input is larger than 4. And the greater than operator is already a function that takes two parameters and compares if the first is larger than the second. So we can partially apply the parameter on the right to get the exact same result. Way cleaner. The partial application of an infix operator is called a section. And I'm not sure if you notice, but we just replaced the second parameter, the one on the right. The cool thing about sections is that you can partially apply the more convenient side. For example, here we are partially applying the concatenation function twice. In the first one, we are partially applying on the right side, so it's the same as creating a lambda function that takes the parameter and adds it to the left of the concatenation. And in the second, we are partially applying to the left. So it's the same as creating a lambda function that takes a parameter and applies to the right. You can do this with any operator. But a warning, the subtraction operator, the minus, is special because you cannot partially apply it. -1 is parsed as the literal -1 number, rather than the sectioned operator minus applied to 1. But don't worry, the subtract function exists to circumvent this issue. Okay, let's go to the final section of the lecture, applying and composing functions. We'll start with the function application operator. If we check how the function application operator is defined in Haskell, it seems a little weird. We see that it takes a function f of type a to b and a value of type a, and then just applies the function to the value. So it looks like this operator is redundant, since it does the same as an ordinary function application. And you know what? It is redundant. However, there's a small but significant difference between the two. The white space operator, this one, has the highest left associative precedence. And the function application operator has the lowest right associative precedence. You can see the difference if we make this evident using parentheses. And as an example of how this changes things, take a look at the following expressions. Here we have a partially applied product operator, and the space operator applies this function to 3 before adding 4. So this is the same as having this. But if we replace this operator with the new function applicator operator we just learned, the right side evaluates first and then the function is applied to the result. Same here. Here we're calculating max of 5 and 4, and here the operator makes sure that the function max is first evaluated with the two of them, and the result, that is 5, gets added to. And here we partially apply max 5 and then apply it to the result of adding 4 plus 2. So we get 6. As you can see in these examples, when using the $sign operator, the whole expression on its right is applied as the parameter to the function on its left. So you can see how using the $sign is like surrounding everything to its right between parentheses. This brings us to the primary use of the $sign operator, omitting parentheses. In the following expression, there are 3 opportunities to remove parentheses, so we remove them. The first opportunity is that everything to the right of show has to be evaluated first before applying show. So we remove these 2 parentheses and use the $sign operator. Same here, this section is applied to everything to its right, so we can remove these 2 parentheses and use the $sign operator. And finally, the same here. This makes your code more readable and easy to understand. Of course, you can do more than removing parentheses, but that's what you'll do the most with this operator. So we'll leave it there and start learning about the function composition operator. We already covered the concept of function composition in our first lesson. So if you're not sure about it, go check it out. But just a refresher and just in a few words, when we compose 2 functions, we produce a new function that is equivalent of calling the 2 functions in sequence when the first one takes the output of the second one as input. We could do this with parentheses. Here, for example, the function f takes as input the result of applying the function g to x. And as a probably overcomplicated example, we could do something like this. Here, we're composing quite a lot, 3 times to be exact. And as you can see, this is quite hard to read, so a diagram could help. We take a list of ints as input, then use take10 to take the first 10 elements of the list. Then use the result as an input for tail that returns the last 9 elements. Then the result of that as an input for filter greater than 25 to filter the values greater than 25. And finally, we take the result of that as an input for any even to check if there are any even numbers left in the list. The diagram helps, but what if I tell you that there is a way to have something as clean and easy to understand, but in our code? This can be done by abstracting function composition to an operator. And because in mathematics, the composition symbol is a ring that kind of resembles a dot, we'll use a dot. Here, we see that the dot operator takes 2 functions, f of type b to c and g of type a to b, and composes them using lambda functions to indicate that the whole f.g expression returns a function that takes the parameter x of type a and applies g to x to get the value of type b, and finally applies f to the result to get a value of type c, this value. It's important to notice that f takes as an input a value that has the same type as the output of g. As you can see, g takes a and returns b, so here g is returning a value of type b that is the value of the input of f. And f returns the same type as the value that returns the composition. So the resulting function takes as input a value of the same type as g's input, a, and returns as output a value of the same type as f's output, c. So now that we have this new operator, how does the complicated f function look now? Well, like this. It's way more readable, and you can tell everything the function does with a quick glance. Also, notice that every function to both sides of the dot operator takes a single argument, or is partially applied until it takes a single argument. If we rewrite the examples from the application operator chapter, but using the dot operator, we get something like this. As you can see, the $sign and dot operators can make your code clearer and concise. But be wary to not overuse them. You could end up having a worse result. And now, as a final way to make your functions more readable, ladies and gentlemen, we present the point-free style. In point-free style, also called tacit programming, function definitions don't declare the arguments. So, instead of doing something like this, where you declare x as input and use it in the body, and here as well, we can do something like this, where you omit declaring the inputs and partially apply the function to get the same result. So, the functions do the same, but now we are not explicitly binding the argument and using it inside the body. That's implicit in the definition, but it's still explicit in the signature. Point-free functions have the advantage of being more compact, easier to understand, and cleaner since they discard redundant information. So we can use the point-free style to change this, our previous complicated f function, into this. As you can see, the only change is that we removed x from both sides. This gives us our final expression of complicated f. This style is particularly useful when deriving efficient programs by calculation and, in general, constitutes a good discipline. It helps the writer and the reader to think about composing functions at the high level instead of shuffling data at low level. This concludes today's lesson. Today we learned plenty of new concepts and ways to improve and combine our functions. It may be a lot to take in at once, but all these concepts are important, so make sure you understand them before advancing with the course. Also, make sure to complete your homework, and I see you in the next one.